Okay, so this is kind of the big new thing that's going on, at least for today, that I intended. It's talking about linear equations and slope, kind of what they mean at a contextual level, because a lot of these problems are nice context problems. The thing that we need to get the hang of is slope is any kind of regular constant change. So when you say dollars per minute or feet per second, those are changes that are consistent. They're considered a slope, a sense of like how fast something's changing. Slope is a sense of kind of steepness or change. So when I look at number one here, very similar to your homework, it says symbolic representation for a linear function that computes. So if I got this long distance phone call thing going, it's 30 cents per minute. If you see something that's like a per minute or a per unit type of measure, it's usually the slope, and any fixed or initial amount is going to be your y-intercept. So it's a really good time to kind of get a sense that that's how slope in a context is a rate of change, how fast something's changing, and it's generally like the y unit per 1 unit of change in the x unit. I'm going to write that here in a minute, but slope is often change in y per 1 unit change in x, and then the slope, the y-intercept, is an initial value, a fixed amount that you start with. So these are great places to kind of see that. Let me define that slope one more time. Slope is change in y. I think of y as being some output variable, your vertical axis one. So change in y, whatever it is, measured in, per 1 unit. So that's why it always is like feet per second. That's per 1 second. Text per minute, per 1 minute, per 1 unit of x. Okay, that's slope. So for ours, and this first one is 30 cents per minute. So that's where we put in the 30 cents per minute. And then the slope goes here because it's taking 30 cents per minute times t, which would be the number of minutes right there. So this is waiting for us to put in, well, if it's 30 cents per minute, well, how many minutes? Well, that's what t's waiting there for you to put in the number of minutes. It's a formula that works nicely if you have a change per unit of time, and next to it you've got how much time. You multiply them together, you get total amount. The only thing is sometimes you start with an initial charge, like a fixed fee. You have to start from, well, I pay $4.95 up front, but then for every unit of t time, what I'm going to do is I'm going to charge them another 30 cents. Now, I've got some unit issues. Now, I wrote that really fast to give you an idea. That's the most common issue that comes up. But you do have to have a consistent measure of unit because this $4.95 is in dollars. And right now, I've got this as cents. Their units have to match between the slope and the y-intercept. So if this is dollars in the y-intercept, that initial amount, then I better do dollars for our slope as well. So that'd be, make those match, dollars per unit. So it's going to be 0.3 instead of 30, because now it's 30.30 dollars, which is 30 cents, a 30% of, or 3/10 of a dollar, or 31/100, however you want to think of it, and then plus $4.95. That's important. Now the next one, they get nicer. Then another way to find out slope is it is a constant change in y per 1 unit change in x. If you see a constant change in y taking place and a constant change in x, you can steal slope from a table of data, but the key is it's got to be constant change. Linear functions are all about data that changes constantly, like with a consistent additive amount. So let's look at this one right here. So as we go, as x hops along, by the way, they both have to change in some consistent pattern. These are all going up by 2 each time. So we got x going up by 2. That's good. Plus 2, k, yep, plus 2, good. So that's consistent. Now if we go down here to y, let's make sure it's also going, now it doesn't have to go up or down, it just has to be consistent. That's down 3. Whoop, down 3 again, that's good, and down 3. Nice. Well, slope is always the change in y over the change in x, and we just saw a consistent change in y of -3 and a consistent change in x of +2. That's our slope, change in y over change in x. So -3/2 describes that change. Now, the y-intercept, this may be one that you remember from that, but a y-intercept is what's the value of x, value of y when x is 0. Now there's two options where 0 happens, but you got to be careful. It is the 1 here That's when x is 0. That's when you have a y-intercept, because then you have a height or a y of 6, not the other one. So the other one's an x-intercept. We want the y-intercept, which is 0, 6. So our formula is going to be, if we're going to write out a linear equation to model this data, since we know the slope is negative 3 halves, you have negative 3 halves x plus a y-intercept of 6. That's our formula. So from tabular data, we can find the slope, the constant change in y over change in x, and then you put x plus the y-intercept, which is when x equals 0, and you can use just the y value of it. Done. Now down below, let's see if we've got another one that models the data. It's got you have to test linearity first, so this is +1, good, +1, good, and +1, bingo. And now make sure these are consistent. This is +3. How about the next one, +3, good, and +3. That constant change in y in a ratio to x, the slope of this one would be change in y over change in x, 3 over 1. For our equation, then, you're going to write y equals 3x, because your slope is 3, and you're looking for when is x 0? What's my y value? That's my y-intercept, and that's negative 3. Done. So now, other contexts, how else you can, it's all about finding the slope and the y-intercept and what's given. So we saw a table, we saw the kind of constant change. We're going to look at this tuition data down here in a minute. We're also going to talk about, in general, how can we look at slope as a measure of steepness or slant? Like, how do we get a sense of what's steep and what isn't? What's our metric for that? And I have some graphs for these problems that will help peel that away for us. Okay, so this is our kind of a good first example, number 6 here. It has some kind of constant rate of change and some initial amount that we're looking for. I'm going to do them and kind of color code it, because here's what I know I'm looking for. I got something x plus something. My slope is going to go before the x, my y-intercept, and after the plus sign there. What kind of constant rate of change are we seeing? So the x is the number of years after 2005, and then the f of x is the amount of chicken that people, pounds of chicken, which is great. So what we're thinking of, if you want to do a graphical representation, or just put a table in there for, or a graph just for a picture, what we're doing is pounds of chicken, and then we're doing the years after 2005. Okay, so that's me using a greater than symbol for after. Now, here goes. In 2005, the average adult ate 51 pounds of chicken. Well, that, since we're starting in 2005, that starting value of 51 pounds of chicken is like your y-intercept. It's when x is 0, when time is 0. Because we're saying 0 right here is, 2005 is where we start this thing. And so that's basically our y-intercept, 51 pounds of chicken. Bingo. Now, the second part, the amount will increase by 0.6 pounds. Now, the 51 was pounds of chicken, and this rate will be 0.6 pounds per year until 2010, is also in pounds, and it's a change, a constant change. It is in y, which is pounds per year per 1 unit of x, that we can see in our graph down below, where our y is pounds and our x is years. Okay, so pounds per year. Definitely a slope measure. But slope is always just constant rate of change that they hand you. So this is 0.6. Done. That's our equation. 0.6x plus 51 is the model for this, where we start with 51 and you get 0.6 of a pound of chicken per year as the consumption increases. Okay. Next one, new situation. Okay, we're looking for the same kind of things. Now this is velocity, and the stone is dropped from a water tower, and its velocity increases at 32 feet per second. Can you kind of see feet per second squared? That's your rate of change piece. And what you want to do is, how can you convert that to, and then it hits the ground with a velocity of 192 feet per second. Now, write a formula for velocity, and there's a little bit more into this problem than you might think of. Velocity is just how fast you're changing, how fast it's going. So velocity increases at a rate of 32 feet per second squared, and then it hits at 192 feet. This might be calling on you to remember some physics, but I have a shortcut for that that might help. And the funny thing is we just need to get to the idea that if you're going to start something, a velocity, what's the rate at which it's changing? What component of information do we get? And there's more physics to this that we could kind of argue, but really I had a rate that I want to put next to t at 32 feet per second squared, plus what was my initial velocity? When you drop something, it starts at a velocity of 0. So it's harder to read in this one, so it ends up just being 32t. So I'm going to take away that 0. But that's to show you that it's a real consistent. If you know that velocity is consistent, it's actually feet per second squared is actually acceleration. And that's the constant change. There is a constant acceleration in our gravitational force. So if you're at a relatively similar altitude anyway, but it's 32 feet per second squared, 9.8 meters per second squared if you want to do meters, but we're doing feet. And that part is constant no matter what. So that's where that goes, that constant rate of change times the number of seconds t. And velocity, when I initially drop it, my initial amount was plus 0 was my initial velocity. So that's just to show you that's kind of a nice thing. And what's our input variable? What does t represent? Input is our t, and it's time. And the domain of this function is to start talking about something. We did domain in some other context earlier, like what x's can be plugged in. Well, now we're talking about not just what can be plugged in mathematically, it's also what makes sense. Like in this problem, what's the reasonable domain? It's not just any old domain, it's just like what makes sense for this problem. There's physical limitations to this question. I am going to start at time 0. I wouldn't do negative time. And the problem says I hits the ground at a velocity 192 with a velocity of 192 feet per second. So that means basically this problem's done once it hits the ground and has a velocity of 192 feet per second. This one doesn't hand me that ending time, but if I know that I'm going to end my velocity, my final velocity is going to be 192 feet per second, and I've got a velocity equation. What I'm going to do is take my 32t, my velocity equation. Okay, I'm going to set it equal to 192, and if I divide both sides by 32, I can get, oh, t is 6. Now, I used a calculator, so don't think I did anything fancy. But that means the reasonable domain of t's that works is when I started at time 0 and when it hit the ground at time 6. I'm not waiting for you to do any crazy physics to figure that out, but I wanted to give you a sense of linear equations are constant rates of change of some kind. The initial amount, the y-intercept, is always what you start at for that particular variable. And then just some fun context stuff that goes with it. All right, I'm going to switch pages, get you some new problems. And this problem is a little bit more approachable just because we have a sense of how it's set up. But what we have are total number of texts, and we've got a t time that's about months if you read through this kind of carefully. So if you get a sense, I just need to write an equation, t of t being total texts, and then we have a sense of rate of change, then it's pretty nice. Okay, this is the function that I'm dealing with, big total number of texts, t, the little t is input in time. There's a rate, 0.6 trillion text messages. I'm sorry, not a rate, but a total number of texts were sent 0.6 trillion texts in the first month of the year, and then after that it went up by a certain rate, 0.7 trillion per month. Well, the rate of change one is 0.7, so that goes with the t, 0.7 trillion per month. It always comes with one of those pers next to it. And then the initial amount, that first month we already had 0.6 trillion, so it's plus 0.6. That's our model. That's it. The rate going next to t, the initial amount going as the y-intercept, that goes right here. Okay. Now, the next piece is what's the domain? Well, we're thinking about time, and the whole thing is, hey, I want to do this for just the first year, and I already have 1 year under our belt, or through the end of the year. And so if you think about it, it's either 0 through 11 or 0 through 12. But for the reasonable domain of this one, we actually have 1 month we already figured out. So we're just thinking about 11 months in. I'm going to do t represents time after the first month. So our domain on this one is 0 to 11 because we're just doing the remaining months in our domain until we get to the end of the year. Okay, so we're just doing 1 year at a time. This isn't meant to make anything scientific. You just look through the problem. It's just trying to give you a sense of domain is just what makes sense for the question I'm trying to answer. It's not mathematically. This is a linear equation. If I graph it, its domain is unlimited. But if I ask for the reasonable domain, my problem is I'm 1 month in. I'm going to get to the end of the year. There's 11 more months to go. So my reasonable t's, my domain, my inputs, would be 0 to 11. 0 being right after the first month, right after January. on up through the rest. Okay, and oh, by the way, C is it asks for the variable. It says number of months after January because that's the context of it. To the next page, I'm going to pull up another problem. Here's a nice problem with just that. If a 500-gallon tank full of water drained at 10 gallons per minute, and you need a model W that gives you the amount of water in there. So just think, where's the rate? Oh, 10 gallons per time unit. And then what did it start with? 500. Done. So that's your formula for this. But the thing is, you have to be really careful. If I were to graph this, it'd be going uphill. That means like I'd be growing in the amount of water. So you want to be careful. The one thing about slope is that if you're gaining or losing from the amount, the rate would be positive if it grows what you start with. It'll be negative if it takes away. And since this is draining, you have to remember it's negative. It also has to kind of graph and make sense. The negative slope makes sense in this situation when you're losing. So keep your sense about you. It's got to be negative, would never be positive. After 3 minutes, so if you put 3, substitute 3 into this problem for t, plug it in there, you get 30. So negative 30 from 500 would give you 470. Okay, so it's just using, can you plug numbers in to make predictions about what to expect in there? Which graph is it? Or back to thinking of 500 as the y-intercept and negative 10 is the slope. Which graph has a y-intercept of 500? Well, it's either A or C. And which one's going down 10 and over 1 has a slope that would get us down 10 over 1, down 10 over 1 as you go. And if you count really carefully, you blow up that graph. It's C has a nice slope of negative 10. The slope in A is just not steep enough. Now the y-intercept is the 500. We've talked about that, but it means the initial amount of water in the tank. It's your initial value, what you start with. The x-intercept is when you have 0, and you can try and look at the graph and figure out where that hits. Or you could actually, there's a way of solving it. You can actually just say, hey, when is negative 10t plus 500? When's it going to be 0? So when we want an x-intercept, we're actually setting the whole graph equal to 0. And I can add 10t to both sides and do a little solving. This is where algebra can help us find out. You can guess and check. I'm sure you could figure it out just looking at it. But I want to know when this whole value is 0. If I divide both sides by 10, I get 50 is the time when it hits a height of 0. So the x-intercept is 50. And then finally, that's when you have an empty tank, by the way. That's the interpretation. And there's a domain question at the end, and it's out of my picture. But then if it's from when I start draining the tank until it's empty, that would be times 0 until this time we just found out, the x-intercept 50. This number represents a time. That's when t equals 50 and when the number of gallons is 0. But that means my domain is anywhere from 0 to 50. Those are reasonable numbers. The graph of it goes forever, but a reasonable domain, or the context, is definitely 0 to 50.